This module is called Radiation Characteristics. And as a dental radiographer, you need to understand how radiation characteristics can affect your dental radiograph. Basically, any change in any of these characteristics, and you are either going to have a slightly better film or a slightly worse film. So, to start with, let's identify what the radiation characteristics are. We have the X-ray beam quality. And if you think of quality, think of it as, the quality of a shirt. When you're going to the store, you want to get a good quality shirt. We want a good quality image. And what factors affect that? When you're buying a shirt, maybe price is one thing that affects the quality of it. A higher end brand may have a better quality shirt than a lower end brand. Quantity, which is a number, and intensity, which is kind of a combination of a bunch of different things. Any variation in these will influence the quality of the overall radiograph. So let's break down exactly what these characteristics are and what they mean. First one is X-ray beam quality. This is the penetrating ability of the beam, or how powerful is the beam. Another way you can remember it is the penetrating power of the beam. So how strong is that stream of X-rays that is coming out of the tube head? This is determined by something that we call kilovoltage. To understand kilovoltage, let's take it back a step and understand what voltage is. Voltage is a measurement of electrical force that causes electrons to move from cathode to anode. It's measured in volts. So this is kind of like electricity. Electricity a lot of times is measured in volts. Batteries are measured in volts. So it's going to determine the speed of the electrons. And we can remember that a higher voltage, remember, determines the speed of the electrons. So a higher voltage is going to have faster electrons and a short wavelength and a powerful beam. And for measurement purposes, 1 kilovolt equals 1,000 volts. So to understand what some of that means, we need to take a step back and understand what wavelength is. It is a part of the X-ray beam quality, and it is something that determines the penetrating power of the beam. So again, how powerful is that beam going to be? Our wavelength determines that. So what is wavelength? Wavelength is the distance between the crest of one wave, so right here, to the crest of the other wave. And where I'm at right now, this is considered a long wavelength because there's fewer peaks and longer distances in between the peaks. So this is a long wavelength. And down below here, we have a short wavelength. So there's more peaks and shorter distances in between. So what again does wavelength determine? Wavelength determines the energy and penetrating power of radiation. How powerful is the beam coming out of the tube head? Our longer wavelengths, remember, more distance in between. Fewer waves, more distance. Longer wavelengths have less penetrating less penetrating power. They are not as powerful. They are more likely to be absorbed into matter. So these wavelengths could be more dangerous to our patients. Our short wavelengths have more penetrating power. That energy is able to move faster, shorter spaces in between, shorter distances to travel, so it gives us more energy. So, how does all of this relate to our dental radiography? Well, it's specific to our units because there's different buttons we can press or knobs to turn if you're looking at this old school picture here that will adjust how that beam is controlled or how much power that beam is going to get. So your typical dental radiography machine is going to use between 65 and 100 kilovolts. So think back that kilovolt, that's 1 kilovolt equals 1,000 volts. So this is 65,000 volts or 100,000 volts. But to simplify it in dental radiography terms, kilovolts. So 65 to 100 kilovolts is a typical dental machine. 65 to 75 kilovolts, that's on the lower end, so it's less powerful. It has less penetrating beam with longer wavelengths. 85 to 100 kilovolts is more penetrating rays with shorter wavelengths. This can be adjusted for individual patients. Again, it's the buttons and the knobs that you see on the control panel. So kilovoltage peak, kVp. Might hear this just as kilovoltage or just kV, but what it is it's the maximum or peak voltage. What is the highest amount of kilovolts that you can use to get that image the way it needs to look? Our kilovoltage or our kVp is going to regulate the speed and energy of the electrons. So in turn, it's going to regulate or determine the penetrating power of the beam. So kVp controls the penetrating power of the beam, which is the quality of the beam. So to repeat one more time, the quality of the beam is controlled by kilovoltage peak or kVp, which determines the penetrating power of the beam. So what else does kVp control? kVp controls density. Density is known as the overall darkness or blackness of an image. It controls the contrast, or how sharply dark and light areas are separated on an image. So how light is one area versus how dark is one area. And the exposure time. Exposure time is the amount of time during which X-rays are produced, or you can kind of think of it as the amount of time that you're pressing the button that operates the machine. So X-ray beam quality controlled by kVp. So the quality controls density. Density, again, it's the overall darkness of the film. If we increase kVp, so we've been saying if we change any of these factors, the image is going to change. So if we increase kVp and everything else stays the same, we do not touch our MA, we do not touch the exposure time, so everything stays the same. The density will increase and the film appears darker. So if we increase kVp and change nothing else, the film will appear darker. On the opposite side, if we decrease kVp and everything else stays the same, our density will decrease and the film will have a lighter appearance. So we have a darker film over here, so this one may have a higher kVp, and we have a slightly lighter one, see the lightness in this area, so the kVp was decreased for that film. X-ray beam quantity is also does control. X-ray beam quantity also controls the contrast. So kVp controls contrast. That is how different we can see the light and dark areas on the film. A low kVp will result in a high contrast image. So there's many areas of black and white and few shades of gray. This type of image is going to be a little more useful when detecting caries or decay. A high KVP image will result in a low contrast. So there's many shades of gray, and it's useful for detecting periodontal disease. Another factor that influences the quality and is controlled by KVP is the exposure time. Exposure time is measured in impulses, so kind of like little bursts within the X-ray machine. So these are like little pulses, little bursts. And as we increase KVP, so if KVP is increased by 15, exposure time needs to be decreased by half. So again, as we're increasing one, another has to decrease because we need everything to be balanced. More KVP means more penetrating beam, means more power. So if we increase KVP, we're going to have more power, which means we need less time to get the image displayed the way we need that image to look. So if we decrease KVP, exposure time needs to be doubled. Less KVP means a less penetrating beam, means less power, which means we need more time to allow that image to turn out the way we need it to be. So now we can move on to the next characteristic. That was quantity. I'm sorry, that was quality. Quality is the penetrating power of the X-ray beam and is controlled by KVP. So now we have quantity. Quantity of the X-ray is the number of X-rays produced in the X-ray unit. So inside that little glass tube where all the magic happens, quantity is the number of X-rays produced inside of there. So we need to back up again and discuss another unit of measurement called an ampere. An ampere measures the number of electrons flowing through the cathode. So on that cathode side, there is the tungsten filament, and the tungsten filament heats up, and when it heats up, it releases electrons from the tungsten atom, and they sit there in that little form, that little cloud called thermionic emission, and that's measured in amperes. Amperage determines the amount of electrons. And we can measure it and break it down because they're small units. 1 milliampere is 1/1000th of an ampere. So quantity is determined by milliamperage and exposure time. So the number of electrons, or the milliamperage, is determined by how long that filament is allowed to heat up or how long that button is pressed. So quantity is determined by milliamperage and exposure time. So let's go back just a little bit further here or dive a little deeper. X-ray beam quantity is measured by milliamperage. The milliamperage regulates the temperature of the filament. The temperature of the filament controls the number of electrons. So, as we have a higher MA or a higher milliamperage, we have an increased temperature, and the hotter the filament is, it's going to increase the number of electrons. And the more number of electrons we have, the higher number of X-rays that we're going to have produced, which means more electrons, more X-rays that can exit the tube. So for example, if we increase from 5 MAs to 10 MAs, that means that twice as many electrons are going to be produced. So we'll have a higher quantity. As a side note here, the average dental radiology machine operates from 7 MAs to 15 MAs. So next we have the exposure time. The exposure time can relate directly to the quantity or the number of electrons. As we increase MA, we decrease the exposure time. Again, as one thing increases, something else must decrease. So we increase MA, we decrease our exposure time. As we decrease MA, we increase our exposure time. So think of it as if you're baking cookies. You've got your dough ready to go. It's rolled out, it's dropped in balls, it's cut out in the cookie cutters. However your cookie is you want to make it. You've got it on the pan and you're ready to go in the oven. Your directions tell you bake it at 350 degrees for 10 minutes. That's what's going to give you that perfect cookie. But we're short on time for some reason. So you're going to bump it up to 375 degrees. If we bump it up to 375 degrees, think of that as your MA. The degrees is equal to MA in this scenario. If we bump it up to 375 degrees, we need to do what to the amount of time those cookies are left in the oven? We need to decrease it. If we don't, we're going to have a burnt cookie. So on the opposite side, our oven's broken and we can't put it at 350 degrees. In fact, we can't bake anything higher than 350 degrees. So we're going to bump it down 325 degrees. We bumped down our temperature. We've decreased our MAs. So we need to increase our exposure time. So instead of baking for 10 minutes, we're going to maybe bake for 20 minutes in this case. Decrease in MA is an increase in our exposure time. This is known as your milliamperes per second. So how many MAs or how is the MAs working with your exposure time? The more exposure time you have, the more MAs you're going to have, the more electrons you're going to have. Our density is also controlled by MA. So here we go. We're increasing things again. So if we increase our MA, we're going to have more electrons. So more temperature. We're increasing our temperature back to our cookies. We're increasing our temperature. We have more electrons, which means we're going to have more power, which is going to give us that burnt cookie if we don't adjust something else. So increase in MA is going to increase our density or give us that darker image. Our last characteristic is X-ray beam intensity. This is defined as the total energy of the X-ray beam. Everything coming together, the quantity and the quality coming together equals the intensity. This is affected by everything. It's affected by your KVP, your MA, the exposure time, and the distance that the beam must travel. For our KVP, a higher KVP is going to give us more energy with shorter waves and more intense beam. This is actually what we want. Remember, thinking back, those low wave, low penetrating beams are going to be absorbed by matter more likely. Those ones are a little bit more harmful to our patients. So we want these short waves with more intense beam. A high MA setting is also going to give us a beam with more energy because more electrons are produced. And for our exposure time, a longer exposure time means more X-rays and a more intense beam. Longer exposure time is more electrons being produced or being released. So that's what gives us more X-rays. So that's what gives us a more intense beam. We mentioned distance. The distance that the beam has to travel is going to increase or decrease its intensity as well. And there's three distances that we need to be concerned with when we begin to discuss our distances here. The first one is the target surface distance. The first one is the target to surface distance. This is the distance from the source of radiation, so inside that glass tube, the tungsten filament to the tungsten target, and then out the tube head. This is the distance from the source of radiation to the patient's skin. Furthermore, as the X-rays travel from the source, the intensity of the beam lessens. Meaning, as the beam exits an 8-inch PID, it is more intense than when it exits a 16-inch PID. That 8-inch is half the distance of the 16-inch, so it's going to be twice as powerful when you use an 8-inch PID versus a 16-inch PID. And that concept is something known as the inverse square law. The intensity of radiation is inversely proportional to the square root of the distance from the source. I always feel like the Wizard of Oz. I always feel like the Scarecrow from the Wizard of Oz when I say that, because he rattles on about the isosceles triangle, and that's what this makes me feel like. But anyway, it's basically stating as one variable increases, the other must decrease. So when we change that PID from the 8-inch to the 16-inch, the distance to the film is doubled. So 8 inches to 16 inches, that's twice. The X-ray beam now has further to travel, and as we've just said, the further the beam travels, the less intense it becomes. So by the time it reaches the film, it is way less intense than when it first leaves the tube head. And if we were to flip that, when the PID is changed from a 16-inch to an 8-inch, the distance is cut in half. So it has less distance to go. So it is 4 times more intense. And the last concept here we're going to discuss is called the half value layer, and this is a part of the X-ray beam intensity. And it states that the thickness of aluminum placed in the path of the X-ray beam reduces the intensity by half. So going back inside the tube head, we had the aluminum filter. Each of those aluminum filters is 0.5 millimeters in thickness. So every time you're adding thickness of aluminum in the path of the X-ray beam, you're reducing the intensity by half. So we have the aluminum filter that cuts the intensity. The distance will affect the intensity. And then it has to get through the patient's skin, through the tooth, and finally to the film. So by the time it is reached the film, it is way less intense than when it originated in the tube head. Let's do a quick review now that we have finished those few concepts here. First question. In dental radiography, the quality of the X-ray beam is controlled by A, kilovoltage peak, B, milliamperage, C, exposure time, D, the half value layer. And the correct answer is A, kilovoltage peak. Number 2, the overall blackness or darkness of a film is termed A, contrast, B, overexposed, C, underexposed, or D, density. The correct answer is D, density. The range of MA most commonly used in dental radiography is A, 1 to 5 MA, B, 4 to 10 MA, C, 7 to 15 MA, or D, greater than 15 MA. The correct answer is C, 7 to 15 MA. I fixed that last slide here, so I'm going to redo, I believe it's question number 3 here. And let me go back in and redo this one. Hang on. Okay, here's the last 2 questions. The range of MA most commonly used in dental radiography is A, 1 to 5 MA, B, 4 to 10 MA, C, 7 to 15 MA, or D, greater than 15 MA. The correct answer is C, 7 to 15 MA. The half value layer is the amount of A, lead that restricts the diameter of the beam by half, B, copper needed to cool the anode, C, glass added to prevent X-rays from exiting the tube, or D, aluminum needed to reduce the X-ray beam intensity by half. Correct answer is D, aluminum needed to reduce the X-ray beam intensity by half.